Welcome everybody to the 2:30, now 2:38 session of our technology tracks. I'd like to introduce to you Doug Plata, an aquatic biologist, an innovator, and more.
Ted Ground.
Oh, I'm sorry, Ted Ground. Excellent. We met Doug. Ted is going to talk to us about a proposed mission to Deimos and an asteroid, I'm going to turn it over to him right now.
How do I do this?
Thank you.
Is that picking up okay? Can you hear me, or should I? How's that? Pocket. Okay. Kind of scared here. First time I've ever done this. The presentation, that is. An auspicious D-type near-Earth object multiple mission, destination Deimos. I'm going to ask you today to use your imagination because that's the theme of our convention. A little bit about me. I'm an Incentive Challenge winner. A couple of years ago, I was invited by the Jet Propulsion Laboratory to give a presentation on the mass balance challenge that I won. It was a NASA challenge that said, if you could hitch a ride to Mars, what would you do? And here I am in front of JPL giving my presentation. Since 2014, I've won 17 of these for a total of $85,000. So I like to think of it as imagination for fun and profit. I'm going to ask you to use your imagination. I'd like you to imagine that you represent the interest of a group of private investors called the Bold Ventures Consortium. I made that up the other day. You are inspired by the daring adventures of those brave souls known early in the history of the oil industry as the wildcatters, like Columbus, Marion Joyner, who found the East Texas oil field in 1930. Exploration oil wells drilled in areas not known to be oil fields were called wildcat wells. Can you tell I'm from Texas? You want to share your inspiration with this BBC group. So you share your vision by reminding them how far and how rapidly technology has progressed in a short time and how it only gets faster, exponentially, moving into the near future. Kind of like Moore's law about computational power, but applied to all kinds of technologies, such as space propulsion. This is the famous spindle top you may have heard of over a century ago. Look at the primitive towers here. Look at the Wildcat Hollow oil well tower here, and the gentleman with the stovepipe hat in western Pennsylvania. This is all part of our development. This has happened exponentially over the period of 100 years. So, nothing ventured, nothing gained, as they say. As the CEO of the Bold Ventures Consortium, I'm asking you folks, would you invest about $1 billion, I'm thinking $500 million actually, to build and launch a multiple asteroid mission into the inner solar system if there was a chance to realize $5 to $10 billion in assets, that is value, within a year or so? So let's say 5 years maybe. Recall that the private sector can launch a heavy lift rocket for $90 million, NASA, $1 billion. Private sector, quicker, multiple reuse, NASA, slower, very costly. You might win your passionate arguments with your CFO and your fellow investors, but you wouldn't know for sure in advance about any returns on your investment until maybe a few years later. But that's okay because you're a wildcatter. No pressure, right? Risk and rewards. Nothing ventured, nothing gained. Auspicious. I titled this Auspicious because it means lucky, but it means a little bit more than just luck. I've packed the definition here with a promising opportunity with potential. And it happens in a fortunate situation. You're favored by fortune, by lady luck, if you will. An auspicious configuration of events will present itself in 2020 when this near-Earth object, 2001 SG-286, which I'm going to call Step 1, please, has 2 close approaches to Earth and 1 close approach to Mars in the same year. It's only going to be an astronomical unit away from Earth around April 2020. It's going to be much less than that around September of 2020. And then, fortunately, auspiciously, it's going to be about 10 million kilometers very, very close to Mars, and that's where we're going to go. That'll be in December 27th, 2020. It'll be a great Christmas gift. So let's hitch a ride, let's learn how to drill, and let's learn how to frack asteroids in the great Texas tradition. Come on. Now, I hope that you can see this. We're going to focus in on closer parts of this, okay? But it's a multi-stage mission to a D-type NEO asteroid and to the Martian moon Deimos. In 2020, if we can pull it off, only the private sector can do it. It's only going to be possible by private enterprise focus and efficiency and by advanced propulsion technology. We're going to start out here sometime around my birthday. I'll be 63 years old. Let's say it's February the 3rd. We're going to start out, we're going to plunge slightly below the plane of the ecliptic. I had to draw this in so that you could see it. It's not exactly a Hohmann trajectory, shall we say, so I just kind of free-handed it, okay? Asteroid encounter happens. Now here's the asteroid path. Please look. It's below the plane of the ecliptic here with the blue. It's above the plane of the ecliptic in the yellow. It's got about a 7-degree angle with the tilt of the plane of the ecliptic. But just like an old-style clock with the hands on it that stops, it's right 2 times a day. And that's when it's right, and that's when it's right. So, April, it encounters the asteroid. It's about a half an astronomical unit away from Earth at that time. It docks with the asteroid. It follows it. I mean, it's on the asteroid, and it's drilling. And it's going to depart when it's also close to Earth around September. It's got plenty of time to learn how to do all that stuff. It's going to get a diploma in drilling because it's going to use it on Deimos. So about a half an astronomical unit. We start out. Let me just go through this a little closer. It's launched from Earth. Its trajectory falls slightly below the plane of the ecliptic, not very much, that of the Earth's orbit around the Sun. It races ahead of the Earth for an April encounter relatively close to Earth, where Earth is going to be in about May of 2020, as seen from above. So within a few weeks of encountering the first destination of our mission, the D-type asteroid Step 1, the asteroid and the docked spacecraft will be crossing the plane of the ecliptic. And perhaps I should say there's more than one spacecraft. It's modular. Remember the NASA administrator that his hair caught on fire when they said that the Mars rover was going to be lowered on the surface of Mars with cables? Well, this is a crazy idea, but it just might work. So what's the big deal about Deimos? Well, it's not size. It's not the dimensions of Deimos that really matter. It's not so much the metes and bounds of the real estate, although it's pretty attractive. Let's take a look. Here's little old Deimos and the limb of Mars. Here's a scale of Manhattan Island, Deimos, and Phobos. Here's a picture of Manhattan Island, a little old piece of real estate that's pretty expensive, I'd say. And here's Big D in my old hometown. At only 495 square kilometers, about 200 square mile surface area, Deimos is only about 8 times the acreage of Manhattan Island, and it's only about half the size of the city of Dallas. These represent metropolitan economies of only about, $1.6 trillion and $5 billion annually. So you can tell your BVC boys that the high rises that can be built, we'll put them below the surface and not above the surface. And this is the new way of flipping real estate. Okay. Location, location, location. Deimos as a destination to Mars. All the D words emphasized. Delta V, it's very low, as you know, at 5.6 kilometers per second. That's low Earth orbit to Deimos, and then 1.8 Deimos to low Earth orbit. The distance and its orbit for a line of sight communication to Mars for around 66 hours, certainly over 24 hours of our time. So if we got a base on there, we can see what we're doing on the surface of Mars. It can be a depot for deposits of dihydrogen monoxide, water. Now, whether that deposit comes from Deimos or whether it comes from elsewhere, it can still be a depot on that moon. And what my thesis today is going to be is that Deimos and Phobos originated in deep space, and the deep freeze of deep space, although they were kicked into the inner solar system, preserved their volatile ices, and that is going to be what's going to make somebody the Exxon Mobil of the solar system. So drilling, let's get cracking on the fracking. Imagination to reality. My assumptions and expectations. Both Deimos and Phobos are D-type asteroids. They were captured into Mars orbit. Deimos is similar spectrally to Phobos' red unit. Studies using visible and IR spectroscopy show that the moon's surfaces resemble D or T-type asteroids or carbonaceous chondrite meteorites. They're volatiles below the surface, folks, even though it might be dry as a bone on the surface. Deep space origins of deep-type asteroids. There was a deep freeze in the early solar evolution. The accretion disk beyond about 5 astronomical units caused a frost line, you might call it, where volatiles were preserved. The Trojan asteroids, that's the asteroids around Jupiter, irregular satellites of the giant planets, and perhaps even Phobos and Deimos, are thought to derive from the trans-Neptunian object population interpretations of the Nice model. The Nice model. The Nice model, named after Nice, France. They developed a model of solar system evolution formation in which they predict, and this is what happened, a large influx of volatile-rich objects from the outer solar system came into the inner solar system. A certain percentage of them did. And the insertion of primitive trans-Neptunian objects into the outer belt took place. And in all of that dynamic gravitational activity that was going on, Mars captured deep asteroids. And guess what? There's a few rare of those that are actually near-Earth objects. They've been spectrally classified, asteroids and comets, into a kind of taxonomic system. I want you to get a copy, if you can, of Francesca Di Mayo's dissertation thesis, and now it is called the Bus-Di Mayo model. It includes 24 spectral types of small solar system bodies. This is based on a principal component analysis of the spectra. It mathematically and hopefully objectively formalizes similarities and dissimilarities of these objects by their observed spectral data. Let's take a look at what our objects of interest are going to look like. This is their John Hancock. This is their nom de plume. This is the D-class spectra. They're linear with a very steep slope, and they have this sort of kink or a slight curvature at a gentle around 1.5 microns. Does everybody know what we're looking at here? This is the wavelength along this axis, and this is the relative reflective reflection. So this is reflectance spectroscopy we're doing here. So this is a key showing all 24 taxonomic classes of small solar system bodies. Well, why are we interested in that? Because Deimos is one of those, and we have a near-Earth object that we can encounter very auspiciously in 2020. That's one of those. Here's a little bit closer view of that. Please get a copy of that. It's really cool. Now, Richard Benzel at MIT has actually shown us in large the spectra of the asteroid in question, which I'm calling Step 1, 2001 SG-286. By the way, this object was on a list for the ESA and JAXA, the Japanese space organization, their multiple asteroid mission. This was one of the objects of interest that they were going to do, but they sat around in committees like they do in Europe, and they never got it funded. And so I think it was also on a short list for NASA to do it, and of course, they didn't do anything either. But it is a good match. It is an excellent match to a D-type asteroid spectra. Now, once again, reiterating this idea of solar evolution and what we would expect to see past the orbit of Jupiter in early solar system development, we have the volatiles preserved outside what we call the ice line. So that's about 2.5, right now in present day solar system, that's at about 2.5 roughly astronomical units from the sun. That's heliocentric distance. So say this with me, the distribution of spectroscopic asteroid types is not randomly mixed, but instead follows a trend with heliocentric distance, as you would expect. The greater the solar input per square centimeter, you would expect volatiles to be preserved. And there you see the D-type asteroids is a percentage of the types of asteroids that are out there. It increases, as you can see, the farther away from the sun. But during solar system evolution, these guys get kicked into the near-Earth environment. That includes Mars and Phobos and Deimos. That is my thesis today. This is more of Francesca Di Maio's dissertation thesis. This is a great thing. Got to get a copy of this. Here's the signature of the D-type asteroids. This is where they are. Here's our friend Jupiter. Here's the Trojan asteroids here. This is where you start to see the dominance of this type of asteroid spectral signature, okay? You don't see any almost in the inner solar system. These are silicate rich. These are ice rich. The volatiles are there, folks, and I think it's both water ice and I think it's ammonia as well. And that's going to be important for Mars development. Ammonia means food, it means atmosphere, it means protein synthesis. Most D-type asteroids are found in the outer main. Uncommon D-type asteroids may represent only 1 or 2% of all NEOs. That's why this is auspicious. I only have 5 minutes, so I've really got to rush through this. But basically, Pascal Lee pointed out that Don Quixote is in between the size of Phobos and Deimos. They're all D-type asteroids. Why not then make Don Quixote? It's a large D-type asteroid. Well, it's way out there, and it has a cometary nature, as you might expect. And that was discovered. And we also see that some evidence, the Soviet Phobos 2, points out to outgassing of both Phobos and Deimos. It has a low density. It has high volatile content, I believe. So why not choose Don Quixote? It's way out there. Its orbital period is 9 years, and it's just not nearly as lucky as drilling into step 1. We have this. You've already seen this, how close it's going to be in 2020. We need to go out there and grab it, and only private enterprise can do it. Where Earth, and Mars are going to line up pretty closely, and it won't happen for quite a long time. Its inclination is only about 7 degrees, 8 degrees. Its perihelion distance is, so it's an Apollo-type asteroid, okay? And its period is 1.58 years. So if you left something on it, you could use it again. It's about as big as an aircraft carrier. So over time, we could literally dismantle it and bring it into orbit, lunar orbit, low Earth orbit, Lagrangian point, whatever, or we could take it by pieces. But we don't know about its mass, shape, surface topography, specific gravity, and we can find out more about that as we go. We would come and depart from the step 1 around September, and I'm putting a short distance on here because I want to push 100 to 1,000 metric tons of water or volatiles to Earth's neighborhood from that asteroid during this period of time. Is your hair exploding and catching fire yet? The main spacecraft, another module, continues on that main asteroid, our asteroid in question, and it jumps off over here. The main spacecraft then undocks from the asteroid when it is only 0.067 astronomical units from Mars, and it's going to go to Deimos and do the same thing that it learned how to do on step 1. I've called it a core sample. I want a cuck mosquito. I want a Bigelow air envelope full of water that'll either stay on Deimos probably, and the other one goes to Earth. Specific impulse, I was going to go through all this, but I only have a little bit of time. So it just simply means the most fuel-efficient way to do things. But we need a flock of hummingbirds and herds of snails. A hummingbird produces this amount of thrust. This is how much a snail can accelerate. To return 100 tons of ice from step 1 to an Earth-Moon Lagrangian point, you're going to need a flock of hummingbirds and a herd of snails. Imagine the possibilities. Imagine Moore's law in electric propulsion taking place. Only the private sector can do this in this short amount of time. The state of the art was the Dawn spacecraft that used xenon gas. It only had a 10 kilowatt electrical propulsion system, and it covered about 31 million miles a month. We're going to do something similar, but on a larger scale. That's what I propose. You could use either a nested hall thruster, a type of electric propulsion unit. University of Michigan shows it here. You could use a Vasimir drive. I know I'm running short of time. You could use a lithium-ion gridded electric propulsion system. You know anybody that's interested in lithium, might be a billionaire? might be interested in space and be a billionaire. This is the way to go, I think, except they're talking about pushing it with a laser. I'm suggesting that it should be done with a nuclear reactor. 58,000 ISP. That's what they say. But they're talking about pushing it with a laser. But it's 20 times better than the state of the art. And it allows the thruster to operate with nearly 100% ionization. It enables very long thruster life, so imagine reuse. Imagine reuse. And here's something cool, the pulsed inductive thruster, a type of ion thruster that could be used to make this cargo system work. It can use ammonia. I think that there are ammonias in these volatile ices. I do. It's going to be deep. It's going to be maybe 20 meters below the surface, but it'll be down there. So, first of all, we need to study step one in great detail with telescopes, from the ground, from orbit, what have you. Build a 50 metric ton payload in the USA, load it up with lithium fuel, power it with a nuclear source, make it multiples of 10K. You got to have probably a megawatt or more to do it, but we can do it between now and January, February 2020. I really believe we can do it. Do it with a Falcon Heavy or a New Glenn Heavy Lift. Shoot it off anywhere in Texas you'd like. Use ion propulsion for 60 to 90 days to encounter step one near the plane of the ecliptic. Orbit or parallel step one for a few days. Decide where you're going to land. Make command decisions. Don't be like NASA and try to figure things out over a committee meeting. And have the gadgets that they're going to take for you to characterize its surface and its subsurface. Dock with it in April. Deploy a drilling rig and start fracking or looking for volatiles. And you know what? If you don't find it, earn a diploma in drilling into a D-type asteroid. That's because you're a wildcatter. Okay? I mean, seriously, we have to take risks in order to make this happen. So, module one is going to depart from step one. So we have multiple modules here. It has electric propulsion. The other one stays on, and it goes on eventually to Deimos. Is everybody with me? Everybody want to do this? I do. Man, it'd be cool, right? So depart from step one with the second set of ion thrusters. Leave drilling rig one because we're going to do some more fracking. Encounter Deimos on December the 26th, 2020 to survey, dock, and deploy it. Start drilling with what I'm calling Plymouth Rock Gusher, or at near one of the poles of Deimos. Collect the volatiles about 10 to 100 meters below the surface into a cuck mosquito or a Bigelow inflated cargo tank or a saran bag. I don't care what you do, but just collect it and leave it there on the surface of Deimos. And that will provide the propulsion and the life support volatiles that you need for your Mars missions, your crewed Mars missions. It'll stay there in waiting on Deimos. So here's a cuck mosquito. The artwork here is by a guy named Nick Stevens. It's pretty cool. And it's showing descending or ascending from probably Deimos. Here's one of Bigelow's operations. That could be full of volatiles. And when we crack open the canister, it's going to have not just volatiles in it, but it's going to have stuff that looks like charcoal briquettes. And the first billionaire that opens that up under the fume hood and takes a whiff of that, it might smell like a wet Cuban cigar wrapped in a soggy diaper. And what is he going to say? Or she? It smells like money to me. The day before something is a breakthrough, it's a crazy idea. And the first trillionaire can be made in space. This is attributed to Peter Diamandis, an advocate and supporter of space who wrote Abundance and Bold. I'm with this guy. But no, I'll settle for half of that in cash. Jimmy Stewart in It's a Wonderful Life. Thank you. This is for my grandchildren and their grandchildren.
Should we take one question?
Any questions?
Time for one question.
Well, my main question is, you didn't mention the Delta V to do this mission. The part where you said that the Delta V relative to Earth of the Earth's orbit was 5.6 kilometers per second was a little bit daunting. That's a lot of Delta V. How much is the Delta V for the whole mission?
Well, the delta V for the step one is like to that of Deimos. When you approach it at the plane of the ecliptic, in April, it's around 5 to 6 kilometers per second. So if you were launching that heavy lift rocket with its payload, a large payload full of lithium fuel, you'd have to impart much of the momentum with the heavy lift rocket, but then you'd have electrical propulsion to carry you through a couple of months. It's already heading in that direction anyway, so the delta V to get to step 1 from Earth is about 5 to 6 kilometers per second, or thereabouts.
And how about physical mission?
Well, if you just stop at Deimos, then it's slightly more than that, because you're going to hop from the step 1 asteroid to Deimos, and that's probably a couple of kilometers per second in my estimation. I'm not an orbital mechanic, but if you were to make this mission just to Deimos and forget about the asteroid, the total delta V would be just about the same, which is about 5.6 kilometers per second, so I understand.
Okay, so you're saying you can get to the transfer orbit for the same delta V as getting...
Roughly, not multiples of 5.6.
And why did you go to that instead of Deimos? When you said Deimos is the target, why did you pick this?
Because of its auspicious alignment, and it's a D orbital, and it is Apollo crossing. It is a D-type asteroid. I believe it has volatiles in it. I think you could take the first module and send it to Earth as a token for everybody that wants to go to the moon first. You'll have an engagement ring around the moon, and that diamond is going to be 100 to 1,000 cubic meters of water from the first asteroid.
But you picked this asteroid as not Deimos, even though you just told me that the delta V is the same. Why this asteroid instead of Deimos?
Jeffrey, you're cutting into my time. I was supposed to start talking 5 minutes ago.
Tell me the delta V to get to Deimos.
Should we suggest you take it up?
Can you guys,
Perhaps
take
we
this
can talk about
outside
it.
and-
Perhaps we can talk about it later. Thank you.
I've got a-